Okay, let me share my whiteboard. Okay, remember what I what I said to you in the first introductory lectures. So about the power processing unit block that includes, let's say, electronic circuits that is devoted to manage a power flow from a source to a load on the basis of a set of control signals in order to obtain a specific goal, okay, at the load side. So we have the power processing unit, and remember that I call this power processing unit also as the converter. Then I said any converter work say in close conjunction with the controllers, the block of circuits that is not devoted to manage power, but devoted to, say, generate the control signal to operate the converter. So we have also the controller. Converter plus the controller. Okay, this is the converter, power processing unit. The sum of the two is typically called the regulator. Okay? Converters plus the controller. So typically there are, as I exemplified in my first introductory lectures, voltage regulators. So means block that accept as input voltage and generate at the output a modified voltage. Modified means, I don't know, that different DC level, or in case of AC voltage, different amplitude and frequency. But of course, also exists several different combinations. And remember that I can add also, I don't know, current regulators. Okay, so sometimes the output is not the voltage, sometimes the output is a current. Okay, for example, when I have to charge a battery, so the battery charger, my output electrical quantity is not the volts, but is a constant current that is given to charge the battery. Okay, so let's focus our attention on the voltage regulators, and in that case, we can have a sort of classification of this kind of circuit. Okay, these circuits are also called power supply. And remember, okay, this is a sort of overview what I already did in the introductory lectures. We can have linear regulator. Linear regulator are made by using transistors that are operated in their active region. Okay, remember that when you operate transistor in active region, this transistor dissipate a huge amount of power due to the fact that simultaneously we have a current flow into the transistor and a voltage drop across it. Okay, so it means that linear regulator, linear power supply dissipates power, so its efficiency is less than 50%. As a positive side, we can say that linear regulators are less noisy than switching regulators. Okay. The other part is the switch mode or switching regulators. Okay, in that case, you have to use, in order to increase the efficiency, just magnetic materials like, I don't know, transformer or inductors, capacitors, and transistors or diodes, transistors that will be operated as switches on off. So that means that the efficiency usually is 100%. These switching regulators can be classified, and this is the new information, okay, into several kind of regulators. Okay? We have the pulse width modulated regulators, the resonant regulators, and then we have, for example, switch capacitor regulators, okay, which is another branch of this switching. So in this course, in what follows, I just focus on pulse width modulation switching regulators. This kind of regulators sometimes are also called ARF switching. Which is the characteristic of these kind of switching regulators? The fact that voltages in these pulse width modulator are switched regulators are always rectangular waveforms. Okay, so voltages are in the for hard switched regulators or pulse width modulated regulators. Voltages typically have this waveform. Okay, so voltages are square waves. They are periodic. Remember that we need a periodic operation of switched mode regulators. Currents are not rectangular waves, but they are, say, linear. Okay, they can be approximated by a set of segments, for example, this one, or I don't know, something like this. Okay, but these characteristics to be a linear variation or almost a linear variation is the feature of this kind of hard switched regulators. Then I have also resonant regulators. In resonant switched regulators, the voltages typically, and also the currents, have, say, sinusoidal behavior, or sometimes you have some pieces of sine wave, okay, that can be connected um, with other sine wave having different frequency, etc., etc. But they are just pieces of sine waves. The difference in the stew behavior is not just having this kind of wafers, but the fact that resonant switched regulators can be operated with even more efficiency that hard switched regulators, because they can be operated in what is called the zero voltage switching mode, or also the zero current switching mode. Okay, there are two different branches for resonant switched regulators. And in this kind of regulators, commutation of transistors that are operated as switch always happens without dissipating any power. This is not a surprise. I said before that I have to operate transistors as switches, because when they are operated as switches, what does it mean? That when the switch is closed, no voltage is, let's say, appears across them, so the power dissipated is null. And when the switch is open, no current flows to them, so the power is not dissipated as well. But this is happens for ideal switch. When you have a real switch, it happens when you open and say close the switch. So when you turn on and turn off the switch with a periodic fashion, there is a huge part of power will be dissipated in terms of what is called the switching or dynamic dissipation. Okay, something that I already mentioned in the first lecture. Okay, so the resonant switch regulator makes possible, okay, by using these two different techniques, for example, to reduce at a minimum the dynamic switching of these real switches inside the regulator. In that sense, I can reduce even more the dissipated power, the switching dissipated power in the switch. And that leads to even more efficiency. Okay. By the way, for this course, we just learn how work hard switch regulator. Okay. So let's talk about the hard switch that passed with modulated regulators. Let's start by another classification. Okay, and this classification is made by talking about the basic topology. So the hard switching regulator can be classified on the basis of the schematic. The basic topologies are basically two. One is the buck converter, which is also called the step down, because the output voltage is always less than the input voltage. Okay, so voltage regulator, and we have hard switch regulators. The buck has this feature: VO is less than P. And then we have the boost regulator, which has the feature that the output voltage is always higher than the input voltage. So for this reason, this boost is also called the step up. Okay, step down and step up. These two topologies are the dual each of the other. Okay, there is a duality in this topology. Then there are some topologies that can be derived from these two basic topologies. And the derived topologies are the buck boost, the buck boost has the feature that the product of VO and VIN is less than 0. So that means that there will be an inversion. If VIN is positive, then VO will be negative. Okay. And then we have another topology which is called the Shook converter, which has the characteristic again that VO and VIN is less than 0, so they have both characteristics. There is some differences in the two. Okay, and we learn in what follows. And again, these two topologies are the dual topologies of the other. Okay? These are the 4 topologies that we learn in next weeks. Okay, and in particular, the buck and the boost, and the buck boost will be also, let's say, regarded by experimental tests in the lab. So think about what you could do in order to follow the time of the lab. Okay, the lab will start next Friday. Okay, so people who are interested, it's not something which is compulsory. Okay, you don't have to do. Okay, if you want to follow the lab, for me it's okay. The number of people that can enter the lab is limited to, I think it's 15 or 18 at the maximum. It's also dependent, I can be more precise, say Friday. Okay, you have to book your seat in the lab in advance. Okay, there are some means in order to record what you are doing. I think starting from the back next week. Okay, I will be more precise in order to the organization of the lab next Friday. So If you look at these topologies here, for example, the boost and this one, this is something that you cannot obtain by the linear voltage regulator. Okay, the linear voltage regulator are the regulator made by, let's say, transistor operated in their active region. Okay, because, for example, for the linear voltage regulator, you can only obtain these characteristics, that VO is less than V. For a linear voltage regulator, you cannot obtain an output voltage higher than V, or an output voltage which has a sign, okay, which is, let's say, the opposite with respect to that of the input voltage. There are other derived topologies, okay. These, if you want, they are the basic, I don't know how to call them, but basic topologies are here. Basic derived topology from these buck and boost are the buck, boost, and the choke. And then there are more derived topologies, and all the derived topologies include a means to galvanic isolate the input from the output. Okay, so these four topologies are not isolated. Okay, but if you want to use isolation, because for example you have to include some safety means in order to protect user, or maybe to protect the supply at the input, and you have to insert some transformer, then you can act on these basic topologies, insert a transformer inside, and then you can have more derived topology. So there are also derived isolated topologies. And these derived isolated topology, I don't know, there is the forward inverter, the flyback inverter, the half bridge, the full bridge, etc., etc., etc. All these topologies will be commented on, explained, and designed in this course. Okay, so this includes some sort of isolation, so a transformer inside it. Okay. Even these isolated topologies cannot be derived, cannot be constructed by using linear voltage regulator. The linear voltage regulator cannot include within their architecture a transformer, and you have to put, say, on the external side, but this transformer can be very heavy, etc., etc. The transformer here can be very small, because typically this transformer will be operated at the switching frequency. Okay, and the switching frequency is in the range of hundreds of kilohertz. Okay, something that I already mentioned in the first slide. So this is our basic topologies. These all this topology, basic, properly said, derived and isolated topologies, can be operated in two different ways. Okay, all switched mode topologies can be operated in continuous conduction mode, or in discontinuous conduction mode. Which is the difference? The difference is not the topology. Okay? The same circuit, for example, the buck circuit, composed by the same architecture, the same elements, can be operated in CCM or DCM. Typically, this depends on the value of the components, the switching frequency, the input and the output voltage, and the load. Okay? This depends on switching frequency, values of components, V in or V out, and the load. This not depend on the circuit. You have not to change something in the circuits to make to operate it in CCM or DCM. Just change the frequency or change the value of some components, and then you can have a totally different behavior. Practically, how can you recognize if a circuit is operated in continuous conduction mode or in discontinuous conduction mode? By looking at the current flowing to the inductor. As you can see in the beginning, any switch mode converters has magnetic components inside it. So, for example, you can have inductors, or you can have in isolated topologies, you can have, say, transformer. Look at the current flowing through these magnetic components. For example, let's have a look at the current flowing through the inductor, which is within the converter. Okay? And if this inductor has a derivative which is 0, okay, time derivative which is 0, then you are in the DCM mode. So you have to look at the time derivative of the current flow through an inductor. I have to say that this is correct, but in almost the totality of the cases, what you have to look is not the derivative of the current, but is the current itself. Okay? If the current flowing through the inductor goes to 0 for a fraction of the switching period, then you can say that this converter is operated in the discontinuous conduction mode. If the current flowing through the inductor is, say, always higher than 0, is always, say, different from 0 for the entire duration of the switching period, then you can say that this current, this converter, is operating in a continuous conduction mode. So the operation is discontinuous if there is a certain time interval in which the inductor current is 0. Okay? By the way, the correct formulation is, say, made by looking at the derivative of the current. Okay, there is a difference in the two formulation. Okay, typically you can look at the current and then you can look if the current is 0 or not during the period, and then you can say certain this is CCM or DCM. But this is not always the case. For example, if you have an inductor, same inductor as before, the same inductor which is included in the converter, and then you short this inductor, okay, what happens? That the voltage across the inductor is null. And you have to remember that the inductor has this relationship between the current flowing through the inductor and the voltage of the inductor. So this means that in that situation, the voltage is null, it's 0, and so the time derivative of the current is null. So this inductor, this converter, the converter in which you have this inductor operated in this way, is operated in the DCM mode according to my definition. Okay, but the IL on the T, which is equal to 0, does not mean that the current is 0. The current can be, let's say, constant, okay, at a certain level, but the derivative is null. So as you can see, the correct definition is, say, made by looking at the time derivative, but for all the totality of the case, it's enough that you are looking at the time behavior of the current flowing to the inductor. Okay, look at the current, and then you can say something about the operating mode. Okay, so this is just a very short introduction about what we'll see in the rest of the next weeks. Okay, basic topologies of switch mode converters operate in what is called the pulse width modulated converter or arc switch converter, and the behavior in these two different ways of operating it. Okay, CCM, continuous conduction mode, and DCM, discontinuous conduction mode. Of course, we have to design these converters in order to design the converters, we have to say analyze in full details every current, every voltages in the circuits of the converter. And this is what I start. What you do starting by the converter, which is called the buck. Okay, so let's start the analysis of the buck converter. That, remember, is also called the step-down converter. Okay. There are any questions about what I said now? So let's talk about the buck converter. Okay, let me share again the whiteboard. The circuit of the buck converter is this one. I have a switch that in this case is a N MOSFET. Let me call it switch. Then we have the diode D, the inductor L. Let's suppose that this is my reference node for the voltages. Let me call this node, sorry, with the name C. This is the node A. This is the output node. Okay. Here you may have a capacitor, which is called C naught, and we have the load. The load is, say, represented by a resistance, okay, R, but this is just a symbol that represents what is connected with these two nodes. Okay, so it's not needed to have exactly a resistance connected there. You can have another circuit. Okay, but what happens here that I can represent it by a numeric resistor with resistance. Okay, this is the output voltage V naught. The current flowing here is the current I naught. Then you have here a voltage V in, and here you can have the current I in. Okay, so remember what I said in again the first introductory lectures about the power converter. I said that one of the main problems in buck converter, boost converter, or the switch mode converter is that they generate a lot of noise because we have switches. Okay? And the switches can be on and off. They can be turned on and turned off very fast and in a periodic way. So that means that I can have very huge di on the T and the T on the T. Remember the slide about the electromagnetic compatibility. Okay? This is something that cannot happen in linear regulators. Okay? The linear regulators, there are no switches, there are transistors in active region, so everything is, let's say, quiet. There is no electromagnetic noise. But here, there is a lot of noise. One of the methods that can be used to confine the noise inside the converter, not to say generate a lot of noise in the surrounding environment where these converters are operated, is to use some specific filters. Okay, filters can be placed at the input or at the output. Okay, typically when you put some filters in the input side, for example here, these filters are made by, let's say, inductance, capacitance, some other structure. Okay, so you can have some low-pass filters that can act on the specific noise frequencies that are generated. Okay, so here I can put a capacitor, which is called C in, the input capacitor, which is the representation of one of the component, the last one component of the, let's say, low pass input filter for EMC purposes. Okay, I know that placing here a capacitance across a voltage seems to be a nonsense, but by the way, you have to take into consideration that Vin is not constant at all. Vin is a source which, let's say, has a source inside it. So the input capacitance is is the means by which I can have, let's say, it can be put in parallel to this Vin because it's not constant at all. Okay? For example, suppose the situation in which Vin is comes from, let's say, a rectifier. Okay, so if you have a rectifier in front of this buck converter, then the voltage across the rectifier is something like this. Okay, so Vin can have, let's say, a variation, okay, across this, across an average value. So this Vin is not constant. So CIN, so the input capacitance, is something that can be put in parallel to this capacitance. Of course, this voltage. Of course, this Vin is totally constant. This capacitance here has, let's say, less meaning. Okay, but anyway, I can regard as this input capacitance as something that remains when I look at some filters that you can put at the input to avoid the, say, emission of electromagnetic noise in the environment. So this is, I can say, CIN is not something that is useful for operating the buck, but in practical circuit is always there for, say, filtering reason. In the same way, the output capacitance has no is not essential to the operation of the buck. Okay, the buck can be operated without CNOT. For example, remember what I said in one of the first lectures. Okay, remember that we already analyzed the circuits. Okay, and I find out that the voltage across the diode is a rectangular voltage, and then I need a filter to extract the average value of this voltage. Okay? But without, if you say eliminate CNOT, you have L and R, which is again a low pass filter. Okay, so L and R without CNOT is a low pass filter. So theoretically, you can operate the buck by using this low pass filter to extract the average value of the rectangular waveform that you can have across the die. But this is a first order low pass filter. And in order to have a very quiet, very smooth, very constant output voltage V naught, this the corner frequency of this first order low pass filter should be at very low frequency. That means that the inductance should be very huge, very large. The same behavior can be done by adding a capacitor here, which now is called C0, and in this case I have a second order low pass filter. Second order low pass filter means that I can have a steep, say, response to the noise, okay, because now in the body representation, the filter cuts out high frequency with a rate of 40 dB decade instead of 20 dB decade, and that means that you can have a smaller inductance having the same filtering action with respect to the first order. So even C0 is not essential to the operation of the buck, okay, this output capacitor is always there, it's always present in the buck because I need to increase the filtering action at, say, the output side of this converter. Okay, of course, discussion can be um, formulated in details with what I discuss later. Okay, just to point out some specific considerations. Okay, the buck can be done simply by the switch, the diode, and the inductor without C-in and without C-not. But anyway, in all practical circuits, C-in for filtering the EMC is always there at the input side, and C-not is always there for, say, increasing the filtering action of the. So, why I put this name here, and also I have a name here, which is the node is called passive. Okay, I forgot about that. I think this is called the active node. A stands for active, P stands for passive. Okay, passive. This is active. C stands for common. Out is the output node. Because it's useful to point out this kind of connection, they will be very useful when we talk 3 weeks from now about the modeling of a converter, the small signal modeling of each converter in order to design the controller. Okay, in that situation, a specific technique to get the small signal model, the converter, is based on, say, this kind of active, common, and passive description of the circuit. Okay, so the active is one side of the switch transistor that is at the converter. The common node is the node which is common between the two switches, diode and the passive is the opposite node of the diode. Okay, so when you look at all the converters, not only the buck boost, the choke, the boost, etc., you always can have this kind of three nodes connected in the same way. So it's like that you have these basic connections that is, say, the same for all the converters. Okay, so get used to this node here because we can use later in these lectures. They are not essential now for describing how the buck works, but it can be employed later on in this the small signal modeling of the converter. Okay, I put here a transistor, okay, which is a MOSFET, but you can use bipolar transistor, IGBTs, okay, whatever. Typically, MOSFET can be operated for because they are very fast, respective transistors, even though the voltage rating of this transistor, the MOSFET, is not so huge, R for the bipolar or the, let's say, the IGBTs. Here you have a diode. Of course, we can have a power diode and a power MOSFET. The symbol for the power MOSFET that I use in this course is this one. Okay, so this is the symbol for the power device. Okay, of course there are a lot of different symbols for the MOSFET, and you can use this one, which is typically is employed for, say, low power analog circuit, or then you can have also something like this for digital circuits, etc. There are every specific application can use different symbol for MOSFET, and this one is specific for power application. Okay. How can we describe the operation of the buck? Remember that I already discussed these circuits, and what I derived in a first, say, introductory lecture was that the output voltage V0 is the input voltage V multiplied what I call the duty cycle. Okay, so we can derive this expression again in a different way. Okay, but consider that we already derived this expression by looking at the average voltage across the diode. Okay, so this is something that we already know. In order to describe the operation of the circuits, let's describe the circuit by looking at two different blocks that are connected inside the back. The first one is what is called the switch network. The switch network is this one. And then I have the filter, or the low pass output filter, which is here, or without CNOT, LR. Okay? So let's start the discussion by looking at the switching network. The switching network is made by the transistor and the diode connected in the way I showed you before. Okay, so let me derive this kind of connection starting from this one. This connection, this symbol, is for what is called the bipositional switch. So a switch that can be operated by means of a signal that I call QA, the unitary switching function, is a logic signal that can be 0 or 1. This is my active node, this is the common node, and this is the passive node. Okay, the three nodes that I defined before. Okay, so when, for example, the logic signal QA is null, then it means that the node C is connected to P. When is 1, the node C is connected to A, exactly as it is shown in the figure. Okay, so depending on the logic level of the unitary switching function, this bipositional switch can be operated in two ways. The same circuits can be operated instead of using this bipositional switch, you can use two switches. Okay. Now this is the common node. Okay. Now the common node has a sense because it's common between the two switches. We have the active node here, you have the passive node here. Now I need two unitary switching function because we have two switches. Okay, but if I use, let's say this is a logical inversion, the NOT. This is a logical signal QA, so it can be inverted. So if QA is 0, okay, if QA is 0 here, it means that you have 0 here, but then you have 1 here. And 1 here means that this switch is closed. Okay, so P is connected to C. 0 means that this switch is open, so it's an open circuit. Okay, so you will get this condition here. When otherwise you have that the unitary switching function QA is 1, then you have 1 here, and then you have 0 here, because there is a logical inversion. In that situation, this switch is closed, and so C is connected to A, and this switch here is open, so you have this condition. So the same operation of the bipositional switch can be obtained by using two switches that are operated in a complementary way. Okay, so what does it mean complementary way? The two switches cannot be closed simultaneously. When one switch is open, the other one is closed, and vice versa. How can you obtain in practical circuits this combination of two switches? For example, by using a transistor and a diode connected in this way. Okay. This is my node A, the common node, this one. Then I have the common node here. and then you have the passive mode. Now you just need one QA, unit switching function, because the MOSFET is something that you can command to be on and off. The diode is a switch which is not controllable switch, in the sense that the diode can be on and off depending on the voltage and currents of the circuits in which the diode is, say, connected. So it's not something that I can command. It depends on other variables in the circuit. So again, I can have here QA, which is 1 or 0. We can see in a short few moments that when QA is 1, the switch is on, so the MOSFET is on, okay, and the diode will be off. When is 0, the MOSFET is off and the diode will be on, okay? How the diode will be on and off, that will be clear in a few moments. But the combination of these two switches, ideal switches, like here, can be obtained by using real practical devices like a MOSFET and a diode, okay? So how many different states can be identified in a circuit when I have two switches? Okay, there are, let's say, basically three different conditions. Different condition can be when this switch, this diode, switch on, diode off. Okay, this is the situation one, and is obtained by the unitary switching function, which is 1. And then you can have a second situation in which the switch is off and the diode is on. Okay, the second situation I already discussed it here. And then you have also another situation, which is a situation in which both switch are off, switch off and diode off. Okay, this is the third situation. Okay, in practice there could be another combination, which is the fourth situation. And the fourth situation is when the switch is on and the diode is on. Okay, this is something that can happen, but this should be avoided because when you have both the switch and the diode on, okay, what happens, for example, in these circuits, in the back circuits, when you have both the switch and the diode on, they can be regarded as two short circuits. Okay? They are fully conducting, and so that means that my voltage V is short circuited. Okay? You are short circuiting the input. So it's something that you have to avoid. Okay, because your converter it could be destroyed. Okay, permanent failures and malfunction. So this situation could be avoided. Okay, but sometimes you can have this part. But basically, okay, you can have these two different situations. Okay, so these two transistors and the diode are operated in what is called the complementary way. And this situation in converter, like in the switch mode converter, are made are say is two one and second situation. These two different state of conduction is operated in a periodic fashion. You have a period, and in this period, you have a part of the period in which you have situation 1, and a part of the period in which you have situation 2. Okay, this means that the unitary switching function is a periodic waveform. Okay, and this periodic waveform is can be divided in two intervals. One in which the unitary switching function is 1, and the other one in which the unitary switching function is 0. And then you have to repeat this period. In that situation, switch is on and diode is off. And in the 0 situation, switch is off and diode is on. Okay? Remember that if I call T on the time interval within the period Ts in which the switch is on, I can define the duty ratio or duty cycle, which is T on divided T on plus T off. T off is equal. So T on plus T off is Ts. And so you can also say that T on multiplied the frequency Fs. Sometimes when I discuss these kind of waveform, so when I have T on, Ts, etc. in a periodic fashion, sometimes it's much useful to rescale the horizontal axis, the time axis, into a dimensionless axis, okay, by dividing time with Ts. In that situation, my axis is rescaled to have here 1 and to have here the duty cycle. Okay? So we can see in some slides that I show you later the time axis, which is rescaled in dimensionless units like this one by dividing Ts. Okay, nothing changed in the discussion. The duty cycle ranges from 0 to 1. 0 when T on is 0, so there is no switch on, and 1 when there is no switch off, so the switch is always on. Okay? So when T on is equal to Ts. Typically, and this is the discussion that I start from now for all the lectures, you can modulate the duty cycle in two different ways. Or you can have a fixed Ts and then you can vary T on, and then you can have a fixed T on and vary Ts. When you have a fixed Ts, so fixed switching frequency, and variable T on, then you have what is called the pulse width modulation. And you are modulating the pulse width. When you have fixed T on and variable switching frequency, then you have something that could be called, let's say, pulse frequency modulation. Okay? But now, starting from now on, I just talk about this first condition. Okay, my switching frequency is constant, and then I can modulate the T on interval in which the switch is on. The switching frequency typically ranges from, let's say, more than 20 kilohertz to also 1 megahertz. Okay, something that we already discussed here. But this is the switching network. Okay, as I said before, the switching network, which is connected to this node, active, common, and passive, is a common feature of all the switching converters. In the buck boost, forward, choke, push-pull, whatever, basic topologies, derived topologies, derived isolated topologies, you can have always this kind of connection. Okay, this is the reason why I stressed the fact on this node here, and I stressed the fact on this switching, because it's something that we can be, say, found out in all the other topologies. Okay, and this is the reason why it's very useful for small signal modeling. Okay, because it's something that you can have in most converters. Problems, questions, something which is not clear. Okay, so I just start talking about the buck converter, describing what's inside in a way that you can find out this block in other converters. Okay, something which will be common in other converters. Okay. The first block that I described was the switching net, but I said at the beginning there is another block which is important in this converter, which is the low pass filter at the output. Okay, so let me show. building block of the convert. Low pass filter. Remember that in the back, the C0 output capacitor is not essential because the low pass filter is already there due to the inductance and the load. In the case, the load can be approximated by a resistor. But anyway, in order to increase the filter reaction, you can pass from a first order low pass filter to a second order low pass filter, having the insertion of the C0 capacitor. Now I have to describe the behavior of the low pass filter by using the switch network concept I just explained. Okay? So this is the back. I have the switch network, can be operated in two different ways. Okay? Switch on, diode off, switch off, diode on. When you have the switch on, now just focus on this switch network without understand why the diode will be on and off, and will be explained in the next lecture, in the next slide. But by the way, I said that there are two different ways that the switch network can be operated. Suppose that the switch is on and the diode is off. The voltage here, the voltage at the node C versus P, is the voltage V in. When you have the second operation mode, so switch off and diode on, what happens here that the voltage is, the diode is on, the voltage here is no. And so this concept, so the voltage across the diode, is already discussed in previous lectures, okay, but now I just mention it in order to understand that if you look at DC over T, supposing that I have a periodic behavior like this, then DC over T is, let's say, something like this. Okay? So it's P in when I have switch on and diode off, and this is almost zero when the switch is off and the diode is on. Okay, so you have a rectangular waveform. Okay, this rectangular waveform is the input voltage of my low pass filter. L, C naught, and the load R. C naught. Okay, so the concept that I already exploited when I used the bucket sample in the first introductory lectures 2 weeks ago is that this filter is designed in order to extract the average value of this waveform. Okay, the average value of this waveform is something that is constant, so the output voltage is exactly the average value. Okay? Anyway, the filtering action due to the low pass filter L C naught is not perfect. In actual circuits, in practice, the output voltage is not exactly a DC voltage waveform. Okay? Because, of course, this filter cannot be filtered out totally, cannot be cancelled out totally. The harmonic contents that are higher its cutoff frequency. Okay? There is a certain attenuation that can be large. Okay? In a second order filter, for sure, it can be larger than for a first order low pass filter. But anyway, you can have a residual of the AC behavior of the input rectangular wave. So what does it mean? That if you look at the output voltage, V naught versus T, you do not have something which is constant like this one, okay? V not here. It's something that can have a, say, behavior like this. Okay, so we can say that V naught over versus function of T as a DC component plus an AC component. This AC component can be indicated in this way, okay, with a hat on top of the V0 variable, or as indicated in the slide, we can also call it our ripple. Okay, V0 ripple is the same way, the same concept. So I can separate the DC part, which is the useful part, and the residual of the AC component of the input wafer after the filtering section. Okay. Typically, what happens here and in all buck converters, that in all the converters, that switch mode converter are designed in order to have this AC part very small with respect to the DC component, which is the variable that I want to get at the output. Okay. So typically, the V ripple or V not at component is much less than the DC component. So I can say that the V not output voltage is more or less the same as V not DC component. This is a very important approximation that I can have in all the analysis that I can have for, say, power converter. It's called the small ripple approximation. So my hypothesis is that this variation here, okay, is very small with respect to the DC component. Okay, this is called here small ripple approximation. Okay, of course, this is an approximation. You have always to think about that we have to say manage real circuits, and in practical circuits, filter reaction is not perfect, and so the output voltage is not a perfect DC voltage, has some ripple on it, imposed on it. But anyway, in a well-designed converter, this ripple is made to be very small. Okay, this kind of quantities of the ripples superimposed onto the usable DC quantities is typical is a specification that designer should be considered in the design. Okay, sometimes you have, I don't know, you have to design a power converter that generates 5 constant volt plus or minus, let's say 1%. What does it mean? That I can accept to have, I don't know, 500 millivolts as 50 millivolts, sorry, as a maximum deviation from this quantity. This is the ripple. Okay. Anyway, you have to take into consideration that this ripple exists. But the small ripple approximation can be useful in analyzing the operation of all the converters. Okay. So let's have a 10 minutes break. Okay, so we can restart at 10:05. Okay, to continue the discussion about that backward. If you have questions, of course, I'm here also in the break. Okay, we started to talk about one of the basic topologies of switch mode power converter, which is the buck, or step down because its voltage at the output is less than the input voltage. What I said up to now is that in the configuration of the buck, there are certain components that are not essential to the operation of the buck converter, but they are, say, practical circuits always present, like the input capacitor, like filtering the noise generated by the operation of the buck. The output is not capacitor to, say, have a better filtering action and not to have large and huge conductors, which is most of the time is impracticable circuits. And we learned that there are two different blocks that can be. One is the switching network, okay, made by switches that generate two these different states, and then the output field. Okay? I just described a means of analysis of the operation, which is based on the small ripple approximation. Let me share again a whiteboard, okay, because I have to point out that the small ripple approximation is something that is defined looking at the V naught output voltage. Okay? So I'm neglecting the small ripple, which is a residual of the alternating behavior of the input voltage DC of the filter, okay, with respect to the DC output quantities that I want to generate, okay. But this made, I repeat myself, with respect to the output voltage. This not means that all other quantities in the converter have no ripple. For example, we learn in a few moments that the current through the inductor EL versus T has a behavior which is like this. Okay, as you can see here, the current through inductor has a ripple. The ripple is the variation you can have superimposed onto a average value. Okay, you have this variation here. Okay, so the small ripple approximation just define about the output voltage. Okay, and this somewhat simplify the analysis we'll learn in a few moments. But the other quantities have ripples. Okay, so to be very precise. Uh, just since we are here looking at the inductor current, which is this one, and we learn how to derive this one in a few moments. This current I show in this whiteboard is a current waveform of which kind of operating mode? Is a continuous conduction mode or it is a discontinuous conduction mode? Since the current is always positive, okay, if you look this current, if you measure this current, if you look in your, say, um, scope, this kind of current, which is all time instant during the period Ts is always greater than zero, this is a current that is generated by a buck which is operated in continuous conduction. Okay, just to continue our discussion that I previously said. Of course, this current can be different from this. Okay, so for example, if you want a current which is typical for a buck operated in discontinuous conduction mode, okay, this current has a behavior which is similar to this. For example, it can be something like this. Okay, if you have a current like this, as you can see here, there is a huge part of the period here in which the current is zero. Okay, and it's zero now. So this means that this current is a current typical for a discontinuous conduction mode operating. There is a boundary between the two. Okay, the boundary is when the inductor current has a waveform like this. As you can see, the minimum current, E minimum and E maximum, when the minimum current touches zero here at Ts, then this is the boundary between the continuous conduction mode and discontinuous conduction mode. If the current goes lower, you have discontinuous conduction mode. If the current is higher than this, Then you have continuous conduction. So this is called boundary conduction mode or critical conduction mode, CRM for short. Okay, so there is the current that goes to zero, but just at one point, not a time interval. Okay, so just to point out what is the difference. Okay, so let me load the presentation. Okay, of course, all what I said is included in the slides that are called back to the state. Okay, of course, this is the slide I just showed you whiteboard. So let's start the analysis of this buck converter. So in order to make the analysis of the buck converter, we have to understand some basic points, okay, that I just, let's say, included in my previous discussion. You have switching network. This is happens for the buck, for the boost, for any kind of switch mode converters. And in order, since you have the switching network, we have different states of conduction, okay? Switch on, diode off, etc. So that means that our circuit is not a circuit which can be, you can call linear because the presence of the switches. So the circuit is something that is, let's say, um, non-linear circuit. But for each of the status that you can have thanks to the presence of the switching network, the converter reduces to a linear circuit. For example, when the switch is on and the diode is off, and you look at the circuit of that specific static condition, the circuit is linear. The same when the switch is off and the diode is on, which is the second possible condition. So you can have, and this is my analysis method, to analyze the circuits for each of the different switch status you can have. In this case, two different status. You can have a linear analysis for one situation, a linear analysis for another situation. Of course, the two situations should be um, made to be continuous. Okay, so you have to understand which is the final condition for one situation, because the final condition for one situation is the initial condition for the successive situation. And so this is very important. And the second situation, the second condition you have to consider is that you have to analyze well, to identify well, which is the succession of the different states. Okay, so what is the method of the analysis of this circuit? You have a nonlinear circuit, but you know that the switches can have two states. Two states. Switch on, diode off, switch off, diode on. For each of these two states, the circuit reduces to a linear circuit that we can analyze. Then you have to say define the initial and the final condition in order to have a continuous analysis. And then you have to identify the different succession of the states. Then I introduce some specific approximation. One approximation is already defined. It's the small signal approximation, sorry, the small ripple approximation for the output voltage. Okay, so I neglect the AC small continuous variation on top of the DC desired output voltage. Okay, because this is my goal. The goal is to have an DC output voltage, so the ripple on the output voltage should be very, very small. Other hypothesis is that all the switches in the circuits are ideal switches. What does it mean, ideal switches? Ideal switches means that when the switch is on, the voltage drop across the switch is zero. When the switch is off, the current flowing through the switch is zero. So they act respectively as short circuit when they are on and open circuits when they are off. In the same way, I can consider that in the dynamic situation, when the switch are commanded to be on and off, so what is called the turn on and turn off, is the time interval which is needed for turning on or turning off the switch is null. So they can be operated in instantaneously to be on or off. Of course, this is not happens in practical physics, but for the analysis leads to very small approximation. For the diode, the same discussion. Ideal diode means that when the diode is on, for me, the diode is on is a short circuit. The voltage across it is null. When the diode is off, it is the same as an open circuit. Current flow through the diode is null. Again, the delay time for the turn on and turn off is null. They can be instantaneously commanded to be on or off. I have to consider also that not only the switches are ideal, but the magnetic and capacitor components will be ideal. This point number 3, I want to discuss a little bit later. Okay, so ideal component means they have no parasites. Okay? The output voltage is constant. What does it mean? Small ripple approximation. I can just consider the DC component of the output and not the AC component. The DC input voltage, Vin, is variable. What does mean variable? Variable means that I can change it. Vin can change from a minimum voltage to a maximum voltage because this is always happens. Typically, the input voltage comes out from a rectifier, as I showed you before. So there is a small AC ripple, so the input voltage is not constant, it's not perfect. This is the reason also why I can put a capacitor across the input voltage, as I said before. And if the input voltage comes from a battery, the battery is not constant at all. The battery can discharge it during the operation, so the voltage generated by a battery is not constant. So the input voltage typically is not considered to be constant. Something that can change from a minimum to maximum voltage. The DC output current, I note, is something that can change, is variable, because the load changes. It's not something, a constant load is something that never happens in practical application. The load is not the resistance I can put in my, theoretical circuits. The resistance is a representation of something that can be more complex. It's simply the ratio between the voltage and the current. Okay? But you can have a circuit connected to the output. For example, if you have a supply for your microprocessor, okay, you have to supply, I don't know, 3.3 volts for your microcontroller microprocessor. Then the load is represented by the circuits that are operating in that particular situation. That depends on the code you are stored in the memory. Okay? So there are situations in which you have the current can be large and the current can be very small. So the current typically is variable depending on the load operation. So if you want, this characteristic is also called for a resistance R, which is variable, it's not constant. Okay? The number 7 hypothesis is that the time constant of the reactive components, of course, in this circuits, you have reactive components that are inductors and capacitors. And then you have this kind of reactive components. You have time constants. For example, for the capacitors, you can have a time constant, which is the product of the capacitance and the total resistance that this capacitor can see from its terminal. Okay, and this induces the generation of a time constant, which is tau, equivalent resistance seen from the terminal of the capacitor multiplied by the capacitor, for example. So the hypothesis, which is in practice always met, is that the time constant of the reactive capacitor are much larger than the switching period. Yes, the switching period goes from, say, 1 over 20 kilos, 1 over 1 megahertz, and the time constants are all. This can, let's say, simplify the analysis. Then, this analysis that I just performed here, and in the next lecture for other basic topology, is for cyclostationary operating condition. Cyclostationary operating condition means that for now, I neglecting transient. What happens when I turn on the converter? Okay, so I just suppose that from the turn on of the converter, a time interval which is enough is say happens that all the currents and the voltages in the circuits reach a steady state situation. Okay, no changes, no transient goals, all transient vanished out, etc. By the way, cyclostationary and steady state are, say, this typical, they means the same thing. Okay? Cyclostationary means that the variables are the same period by period. And this is the case, because as you can understand, there is a period which is Ts, in which you have a variation of some electrical quantities. I showed you before as a variation, but this variation is the same for each period. So this is a cyclostationary condition. Typically, steady state can be employed for something that is always constant. For example, the output voltage is anyway. We can use both the names, okay? Cyclostationary or steady state. So these are the basic conditions that I'm using to develop the behavior of the buck. Okay. So let's start the analysis of the buck converter. And so let me share again my whiteboard. Okay. So I have the buck circuit. Let me replace the MOSFET switch by an ideal switch. Why I can do that? Because one of my hypotheses is to consider the switches to be ideal, so like ideal switches. Okay? So I can do that on the basis of my hypothesis. This is R, the load V naught, I naught. The current flowing to the inductor is IL, this is D. I have C in and I have V in. Okay, this is my switch. So remember, I have to identify two linear circuits, and I can find out a linear circuit for each of the two status that can be derived by looking at the switching network. So let me show what happens during the first part of the period, which is the part that happens for a time interval during T on. Okay, during T on, what happens? During T on, the switch is on. So what happens? That the switch is closed. Okay? Since my hypothesis that the switch closed has no voltage drop across it, the voltage across the diodes, the voltage across the diode means the voltage here, I call this common node. So the voltage VC in this time interval is the same of the input voltage, is V in, which is positive. So I have a positive voltage from the cathode to the anode of the diode. So what does it mean? The diode is off. As I said before, while the switch can be commanded by the unitary switching function, so there is a driver, a gate driver, that is commanding the switch on and off. The diode status depends on the, say, voltages and current in the circuits. Okay, and in that situation, the voltage across the diode is a voltage that reverse biased the diode. So the diode is off because it is reverse biased by the voltage being. Okay, so the diode is off. The diode is off, and my hypothesis is that the diode is an ideal diode, so I can replace it by an open circuit. Okay, in that situation, what happens? The current flowing to the switch is the same as the current flowing to the inductor. Okay, the voltage across the inductor is here. You have V in, as I just discussed, and the voltage here is V naught. So VL is V in minus V naught. Now I have to use the small ripple approximation. VO of T for me is a constant voltage because I neglect the ripple. So is V in minus V naught. Look, the capital letters here means that I can use average value, I can use constant value. Okay? V in minus. This is the voltage across the inductor. In that phase, in this phase, which is the phase during T on, what happens? The voltage at input is, say, the power from the input transitates here, okay, and charges this capacitance here. Okay, so in that phase, energy is provided to the output side of the converter, okay, because there is this specific connection. In that situation, which happens only for this time interval here, the circuit is linear because the switch are, say, in the conduction state for the switch or in the interdiction state for the diode. Okay, there is no variation of the operating condition of these two switches. Now this situation is linear situation. So I can examine this situation with the usual method. Okay. Remember that VL is V in minus V out. I put here this sign because I use a small signal approximation, small ripple approximation. So no, it's constant. VL is the inductance, and then you have this specific relationship for the inductance. So L in time derivative of the current. So what does it mean then? The time derivative of the inductance current is V in minus V naught divided by L. Okay? Since we have a ratio of constant quantities, I can say that the current through the inductance is rising up. Now, suppose that we are talking about the continuous conduction model. Okay? So let's start discussing this situation. Let's continuous conduction mode. Okay? See. So what does it mean? The inductor current never reaches zero. So at the beginning of the period, the current is not zero. For example, you have this current here. The period is Ts. But now we are focusing our attention about the time interval T on, which is this one. This is my period of interest, okay? If you want, this is the period that I call number one when I look at the switching network status, okay? The current rising up with this slope. This is the slope. The current is rising up in a linear way. The slope here is VE minus V naught divided by L. So it depends on these quantities. V in, V naught, and inductance. We can call this current minimum inductor current, and this is the maximum. Okay? I said before that the switch current is the same of the inductor current. So this is also the switch current. So if I put here current through the switch, this is yes, this is the on, then I have the same current here. Okay, for the switch and for the inductance. Okay, so if you want to describe mathematically the behavior of the inductor current, we can say that you have a minimum current plus what, using this expression here, is 1 over L, the integral of the inductor voltage. So is the minimum current plus V in minus V naught over L multiplied T. Okay? Of course, for T, which is included in this time interval, 0 to T on. Okay, so this is a linear variation in this way. Let's have a look to the voltage across the switch. The voltage across the switch in this phase, so we are talking about this phase here, is closed, is on, and for my original hypothesis, the voltage is 0. Okay? The voltage across the diode look at the circuit. Here. As you can see, you can define a voltage VD from the anode to the cathode. Okay, so the voltage across the diode is negative 2 minus V in. The current through the diode, the diode is off in that phase, and so the current through the diode is. Okay, I hope that this should be very easy to follow. Okay, so this happens up to the time t on. That in that situation, the switch is commanded by the unary switching function to be off. So now starts a second phase, the phase number 2 in the switch network operation, and the phase number 2 that happens from t on to Ts. The switch is off. Let me redraw the circuit. So the switch now is off, and by hypothesis, the ideal switch can be considered as an open circuit. I have here C in, V in. This is the inductor with the current inductor IL, that is C naught. And the VMR. Okay. So let me draw the diode in this way. Okay. What happens in that phase? The switch is off. Okay, so the current flowing to the switch is null. Which is the current flowing to the inductor? But you have to consider that, as I said before, in the transition between one state, one linear circuit defined by one specific operating status of the switches and the successive, the final condition becomes the initial condition of the successive phase. So, which is the final condition for the inductor current? The inductor current reaches this value that I call Imax. So, the current flowing to the inductor is positive. So, what does it mean that the current is positive? Current positive means that at the very starting point where I command the switch to be off, here this is a current which is different from zero. The inductor opponents to the variation of the current, always. The inductor tries everything in order to maintain the same current flowing to the circuit. In another way, you can look at the same situation, looking at the energy. When you have a current flowing through an inductor, it means that you have an energy is established in the magnetic field of the inductor. And this energy is 1/2 L multiplying the current flowing to the inductor square value. And you should know that energy cannot disappear suddenly. Okay? So, this energy cannot be made instantaneously equal to zero. The inductor tried everything to hold the same current it as before. So the initial current from the inductor is the same of the final condition for the current. So at the beginning of this situation, the current from the inductor is always different from zero. So imagine the situation in which the diode is still off. Where this current can flow since this diode is off? And the current instantaneously should become zero. But this is not possible because you have to say an energy that cannot be disappeared, or in other terms, the inductors try to have the same current. So the only way to maintain a current flowing is to turn on the diode. So the diode becomes on because it should provide a path for the current of the inductor that tries to continue to follow in that situation. So if some one of you ask why when the switch is off the diode is on, now the answer is that when the switch is off the diode is on because it acts as a freewheeling path for the inductor current. This is also named for this diode. This diode is called freewheeling diode. It means that it provides path for making the current in the inductor circulate in the circuit. Okay, so this provides this kind of path. So the diode is on, and if the diode is on, the current in the diode as this, the current is the same of the inductor current. In this phase, the inductor current is the same of the diode current, okay? While the current through the switch is zero. In that situation, what happens to the output voltage? But the output voltage is maintained at the constant value due to the fact that these output capacitors and the inductance, so the filter, accumulated the energy in the previous phase to maintain the output voltage to be constant during the T-off phase. And so the energy now is provided by the inductor and the capacitor to the circuit. Okay? While the previous phase was the input that provides the energy to the output side of the converter, now is the output side, the reactive elements that stored energy in the previous phase, that are now release the energy to the load, maintaining the load voltage constant. Okay, so the switch is current to switch is 0, which is the voltage across the switch. The voltage across the switch is simply V in. So this switch is equal to V in. This is the voltage across the diode. Voltage across the diode is null because the diode is on. Okay, and since I consider it as an ideal, I consider it as process, which is the voltage across the inductance. The voltage across the inductance now is the voltage across the diode minus the voltage at the output. Okay, simple Kirchhoff law, this mesh is the voltage across the diode minus voltage across the output. But the voltage across the diode is null, so it's minus VO. And since the small ripple approximation holds, I can say that VL is more or less the DC voltage of the output. Okay, so what happens to the inductor current? We have switching period, then I have T on. Remember that I already defined a linear behavior between Emax, Imin and Imax during the T-on interval. The slope here was V in minus VO divided L. Remember that we are talking about a buck in which VO is less than V in, step down behavior. Now the voltage across the inductor is minus VO, okay, so is negative. So it means that I have a slope which is negative. The slope is minus or negative V naught over L. Okay, negative V naught over L. Slope. Okay, with the same reasoning before. What happens to the current? The current at the end of the cycle must go to a minimum value. Why? Because we are talking about steady state or better cyclostationary situation in which no transients would be considered. Look at what happens if I consider the situation in which the current at the end of the cycle is not exactly I mean. For example, is less here. Okay, so that means that, sorry, the current is let me change the color just to. Now suppose that the current goes here. What happens in the next cycle? Next cycle has the same behavior as the first one, same slope, say time interval T on, and then the current goes down. So I have a situation in which the output current is not constant, so the inductor current is not constant cycle by cycle. So the situation, the blue situation, is something that is not cyclostationary condition. Cyclostation means that they have no transients. Okay, so using this hypothesis, I have to say that the final current through the inductor should be the same of the initial current through the inductor, okay, due to my cyclostationary steady state condition. Okay, so cycle by cycle, I have the same way. Okay? So I mean is the same of this current here. I max is the same. Okay. So this is what happens to the current IL. What happens to the current, for example, through the switches? To the switch, the diode switch, sorry, the MOSFET switch. What I said about the switch current during the T-on phase. During the T-on phase, the current to the switch is here is the same of the inductor current. What happens during the T-off phase? The current to the switch is null. So I have a situation in which the current I switch is equal to IL during T-on, but it's 0 during T-off. From I minimum to I max. Okay? What happens to the current through the diode? If you look at the current through the diode during T-on, current through the diode during T-on is here, is the yellow one, is null. What happens to the diode current when we are during T-off? The diode current is equal to IL. So if I look at the diode current, let me have the diode current at the bottom of this graph here. I have 0 during T-on, and then the same current of the inductor during T-off. T-on, yes, this again is I min and this is I max. Okay. What happens to the I don't know, the voltage across the switch? 0 during T-on, of course, because the switch is closed, and V in during T-off when the switch is open. For the V switch, I have during T-on is null, V in during off. What about the voltage across the diode? The voltage across the diode is minus V in. Minus V in is the green one during T-on, and of course would be 0 here when the diode is on. So it's minus V in. Then what I miss, I can say that all the way from here. As you can see here, I analyze the circuits by dividing the nonlinear circuits, which is a switch mode circuit, so it's linear for each of the different operating conditions of the switching network. And I consider that all the final conditions, for example, in this situation, it's very important, the final current into inductance for each phase as an initial condition for the successive phase. And I, in a period Ts, alternated the situation in which the switch is on to the situation in which the switch is off. Okay? If you want to describe the current here, mathematically, as we did for the T-on phase, we have that IL over T is I max plus again the integral of VL tau in the tau, which is I max minus V naught over L. And this happens for T, which is included in T-on. So there are questions about this description. As you can see, the description, the operation, the analysis of operation is not so complex by using the hypothesis, for example, the small ripple hypothesis and considering ideal switches, and by dividing the interval into two linear operating sets. Okay. Questions, doubts? As you can see here, all the waveform I discussed are already present. So let me now share again the whiteboard to discuss another waveform that I in the circuits which is not described, which is the inductor voltage waveform. Okay? The inductor voltage waveform is something that we derived for the current. Okay, so I derived, for example, that the voltage VL is minus V naught, negative V naught in T off, or is V in minus V naught for the T on. Okay, let me plot this voltage. Okay, here, TS and T on is here. So let me have this discussion with V in minus V naught, and then I have negative V naught, something like this. Negative V naught here. Okay, this is the voltage VL. Okay, and by using this voltage level, I derived the slope of the inductor current, etc. Okay, but this voltage waveform is also important for another concept which important in the description of the converter, which is called the voltage let me say the inductor voltage second balance. It is the inductor voltage second balance. It is derived from the relationship between the current and the voltage in inductors, which is VL, L, time derivative of the current area. Let me integrate this expression in a period Ts, okay, in a period Ts of 0. What happens if I integrate this expression? I have L time derivative, integrate it over Ts. It means that I have IL Ts minus IL 0, which is 1 over L of the integral during Ts of VL. Okay. This difference here, IL at the end of the switching period minus IL at the beginning of the switching period. Look at the current here. In steady state analysis, cycle stationary conditions, this means that these two currents are the same. Okay, IL at Ts minus IL at 0. So these two currents will be the same. So that means that this difference is 0. So it means that this integral is 0. So the integral between 0 and the switching period of the voltage across the inductance will be 0. Now what happens if I multiply these 0 quantities by a non-zero quantities? Nothing changes. So if I multiply by 1 over Ts, this quantities is again 0. So let me nothing changes. This is 0, and multiplied by a non-zero quantity is again 0. And now this quantity is here as a meaning. This quantity here is the average voltage across the inductors. Or in the following, sometimes I can put a bar over the variable to indicate the average value over the period, or sometimes I can also use the capital letters, okay? The same for me, this means DC quantities, okay? So the average value of the inductance voltage across period is null. So in a steady state condition, the inductors do not have any DC component. This is very important. This is exactly what is intended for volt-second balance for the inductor voltage. Look at the voltage here. This is the voltage of the inductors. We are in cyclostationary condition, in steady state, so the inductor voltage second balance holds, meaning that the voltage, the average value of the voltage across the inductor is null across a period. So what does it mean? That these two areas here should be the same. The yellow one and the blue one, these two areas should be exactly the same, because when they are the same, the DC component, the average value of this weapon is null. So this is the area A plus, this is the area A minus. So according to this concept, okay, A plus should be the same of A minus. Let me discuss what is A plus and A minus. A plus, the area A plus, can be derived by a single rectangle area, okay, which has a 8 of V in minus V naught multiplied what? Let me redraw just for commodity value. Minus the voltage across the inductor. Okay, we have V in minus V naught, and then I have V naught negative Ts and T on. Okay. Remember, this is the voltage across the inductor VL. Okay. So, as I said before, nothing changed. If I rescale the time axis dividing T by Ts, in that situation, this is no more Ts, this is 1. Okay. This is no more T on. This is the duty cycle, D, because T on divided Ts is the duty cycle. Okay. So this time, sorry, this interval now is D, and this interval now is minus minus. Okay. This is because I rescaled directly. So the area here is A plus, is V in minus V naught multiplied D. The area I minus, which is this one, is simply V naught multiplied 1 minus T. The two areas should be the same for what I said before, because the DC voltage across the inductor in cyclostationary situation is null, so that V in minus V naught should be V naught 1 minus T. Okay. Solve this expression for the output voltage V naught. If you do this, you can find that V naught is equal to D multiplied D. Okay. Remember that this expression was already derived. Okay, when in introductory lectures I define use the buck as an example for switching converter, I derived this expression. But I derived this expression by looking at the DC value of the voltage across the diode and then extracting the average value of this voltage. Okay, remember that this is also something that I brought here. Okay, remember, this is exactly the expression I derived in the first lecture. Okay, look at this. slides in order to understand in which way it's been derived in that situation. There's a different way. Okay? But in the two ways, the result will be no difference. Okay, in that situation, I pointed my discussion, my analysis about the extracting the DC value of voltage by the output field now by using the volt second balance inductor. V naught over V in, which is D, is called the conversion ratio. Okay, this is one of the most important parameters of the converter, which is the conversion ratio. So the conversion ratio of the pack M is equal to the duty cycle. When for CCM operation, okay, so maybe it's better to put here a conversion ratio for the continuous conduction mode, because we are just analyzing what happens when the inductor current never reaches zero during TS. Okay, so continuous conduction. So now that we obtained these important results, so that continuous conduction mode conversion ratio is D, now we can derive the small signal parameters that I defined in the introductory lectures as important parameters to classify, to evaluate the performance of converters. Okay, remember that we have the audio susceptibility, which is the derivative of V naught as a function of V in. And since this is my expression, and then this is V naught over V in, this audio susceptibility is exactly the conversion ratio. So it is V. So the audio susceptibility is like the duty cycle. Okay? It's a variation that is the same of the duty cycle. The fact that the audio susceptibility is the conversion ratio is always the same for any kind of converter. Okay? Then in the back case, CCM mode, this conversion ratio is equal to this. This second equalities depends on the converters. Okay? But the first one, this one is common for all the converters. Small signal output resistance is the quantity V naught variation over I naught. If I look at the expression of V naught, which is indicated here, there is no mention about the output resistance, output current. So I can say that the output resistance of the buck in CCM is null. Okay. Then we have the gain. The gain is defined as delta V naught as a relation of the duty cycle, so the control quantities. Okay. And this is again derived by this expression, and this is the input voltage. So the gain depends on the voltage gain. So it's range of the gain as is not dimensionless. Okay, it is a voltage quantity. And then the gain now is the voltage gain, and the voltage gain is something that can change. Remember that I, as my hypothesis, my first hypothesis, I said that the voltage gain, which is say considered to be varying between a minimum and a maximum value, for example, because which is charging or say rectifier output, etc. The gain depends on the input voltage. Okay. So I discussed the introduced what I call the inductor voltage second balance. Okay, so the fact that in cyclostationary condition, the average value of the voltage across the inductor is always null, so no DC component of the voltage across the inductor. But again, it exists the duality theorem for capacitor. Okay, and for capacitors, this is called the capacitor balance. And so it's something that is like the voltage second balance for inductor. Now it's for the current flowing to the capacitor. Okay, it would be useful for successive analysis. Okay, so let's say without notes. IC in general can be expressed as the multiplication of the capacitance value and the time derivative of the voltage equals this capacitance. What happens if I integrate it over Ts, over a period? It happens that we have dc at time Ts minus dc times 0, which is 1 over C integral over Ts of IC t in dt. Okay, so we get the same steps we made for the inductors here for the capacitor. For in the second stationary condition, it happens that these two quantities, Vc at time Ts and the voltage equals the capacitance at time 0, is null for the same reasons that leads to the, say, IL Ts minus IL0 equal to 0, because we are in steady state. There is no possible any transient occurring in the voltage and current wave. Okay? So it happens that this integral is null. So what happens if I multiply this one for 1 over Ts? Nothing changes because the integral is 0. But this has a physical meaning. This is the average current flowing through the capacitor in steady state. So the average current flowing through the capacitor in steady state, that I can express with these different symbols, the bar on the capital letters, is null. So in steady state, no DC current can flow through a capacitor. Okay, this is the capacitor charge balance. So this is the dual, let's say, principle that I already derived for the inductor. The inductor is the DC average voltage because the inductor that should be 0. Now this is the DC current from the capacitor. Why is important these quantities? Because we have to derive another current which is not already derived, which is the current flowing through the C0 capacitor, the output capacitor. Let me derive the expression of the current flowing to the output. So in this case, let me just draw the output side of the buck converter. Okay, so the side which is composed by L, C0, the load, I0, is which, IL, and IC0. Okay. In particular, I know that IL has this waveform in CCM. From I minimum to I max. Okay, the variations are linear. And what I can say here, this node, the out node, remember this is the name. In the out node, I can use the Kirchhoff current law. Kirchhoff current law says that IL of t is equal to I0 plus I0, IC0. But this is a quantity over which I can put a bar, so I can average it. What happens if I average it this information here. If I put the average of these two quantities, okay, I can have a linear operator. And the current, the average current IL is equal to the average current I0 plus the average current IC. Now, okay, because it happens that since these kind of quantities, the instantaneous values are summed up in this way, you can use also the Kirchhoff current law for the average value, okay? And you can use this quantity here. So, which is the average value across the capacitor? We are reasoning about steady state condition. The average value across the capacitor is null. Okay? The average value of the current through the capacitor is null. This is the charge balance for C naught. Okay? So what I can say that the average value of the inductor is the average value of the output current. Which is the average value of the output current? The average value of the output current is the constant current because this quantity here, V naught, for the small signal, sorry, again, small ripple approximation, this is a DC quantity, okay? So I can say that IO average value is simply V naught over R, so let me call it I naught. Okay? So the average value of the inductor current is output current. Okay? The average value of the current flowing through the inductor is the output current because no DC current can flow through the output capacitor. So which is the current flowing through the capacitor C naught. Okay, I C naught. I C naught over T will be IL minus I0, I naught. But I naught is the average value of the inductor current. So the current flowing through the output capacitance, it can be derived simply by looking at the inductor current etc. Okay. Considering that the average value is exactly I naught, and so the current flowing through the capacitor is simply IL minus its average value. So IC naught is the red curve centered around zero. This current here has no DC quantity, okay, no DC quantity, is just an AC waveform, so no DC value. This quantity can be called delta IL, and this variation is the same that you can have here, delta IL. Okay, the period is this one, but the current through the output capacitor is given by this. Okay. Remember that delta IL is the difference between the maximum current minus the minimum current across the inductor. Okay, we have discussed here. Okay. I max minus I minimum. How can we found this delta IL? Look at the inductor current. Okay, the same value at the beginning, the end of the period. This is I minimum, I maximum. This is T on, this is Ts. Remember that I have this loop, which is negative V naught over L. Okay, so how can derive this delta EL? Delta EL is equal to, I know the slope here, which is V naught, negative V naught minus VL, and this happens for the time interval, which is called as T off. So I can say that delta EL is V naught over L multiplied T off. But T off is Ts minus T on. So is Ts 1 minus D. So T off is 1 minus D over the switching frequency. So this is V naught over L, 1 minus D over L. Okay, this is the variation. This variation is called also the ripple current. Okay, this is the inductor ripple current. Inductor ripple current depends on the frequency, depends on the duty cycle, the output voltage, and the inductance. Using this ripple current, you can also say that the maximum current is equal to what? The maximum current is, since we know that the average current in the inductance is the I naught current, I can say that this is I naught plus f the value of IL, and E minimum is I naught minus delta L over 2, where I naught is V naught over R and delta L is the current here. Over R plus 1 F VO over R 1 minus V over L switch, and the minimum current is V naught over R minus 1 F VO over R 1 minus V S. Okay. I can stop here the lecture for today. Simonetti, Marco, have you had some problem in, say, looking the slides? Can you see some more? It's okay, okay. If you have problems, you can ask me. I didn't see your comments in real time. So let's continue next Friday afternoon at 2:30 p.m. This discussion, okay? Starting exactly from this point, okay? If you have a question, I can answer now your questions, or maybe later by email, whatever. No questions? Okay. Thank you for your attention. See you next Friday. Bye.